welcome. We are back today, assembly language part 4. I think this is it for the assembly language. Well, Julie's got some assembly on Friday as well. We have taught you a lot of stuff this week. We're going to wrap most of it up today, and then this week is an assignment called the binary bomb, which is kind of a fun one, so hopefully you guys will enjoy doing that. And it is going to be due after the Thanksgiving break, but that doesn't mean you should wait until next week to start it. You should probably start it this week. And I have a feeling that office hours this week may be slightly less attended than normal, so it would be a good opportunity to get some help on the assignment. All right, so let's talk about what we're going to do today. There's some reading from class. We've kind of finished up the reading. In fact, I think I actually have a different reading here and here. No. Hang on. I think I do have the wrong reading there, but we'll see how it goes. So anyway, there's 3.10, which is also 3.10, which is also something that you should be reading as well. So we're going to continue talking about assembly language today. What I'm going to do is I kind of rushed through some of the stuff at the end of class on Friday. So we're going to go back to some of that again and go through it a little bit slower so you see some of the assembly in action for, in particular, the procedures for storing things on the stack, storing things in registers, and then we'll move on from there. And then today we're going to talk about arrays, structures, alignment, function pointers, which I know you guys love so much. And then we will, that'll wrap it up. All right. So as I said last time, so this is a bit of a review from Friday, but the idea is I didn't do it in quite enough detail, I think. So we've seen like storage in registers, but sometimes you need to store things on the stack. And when do you do that? When the registers don't hold the data, the local data. Also, when you have the ampersand symbol, you have to store something on the stack because there's no other way to reference it. You can't have a reference to a register. Okay? Another time is if you have arrays. Well, arrays take up more space than just one single data type, so you have to have that on the stack as well. Structs, which we'll talk about today, same thing. Okay? How do you actually do the allocation? Well, you decrement the stack pointer and you put the stuff on the stack. Remember, the stack, you have all of the space underneath the stack pointer. Like if you subtract from the stack pointer, you've got all of that space to use, and that's how you actually go about doing it. Okay? But remember, at the end, your stack pointer has to point back to where it started, so that, remember, the function that called you has its next instruction waiting on the stack for when you do return, then that ends up back there. Okay? So let's actually go through this. The same example that was the other day. Let's just do it in a little bit more detail here. Okay? So what do? Let's look at the function that we're doing first. We are the caller function here. Okay? This caller function sets up a couple arguments, and then it, here, I'll sit down for this actually, sets up a couple arguments, and it puts the arguments, as it turns out, onto the stack because the compiler's smart enough to know, oh, guess what? I'm about to use them with the ampersand operator in there, so therefore I'm going to have to put them on the stack. Okay? Otherwise, there's no way to give the address of a register when you're passing into a function, so we do it through the main memory system. All right? In this case, on the stack. All right. And then, so it takes those two and it puts them both on the stack. The first one goes right at the stack pointer. The second one actually goes to 8. It goes 8 away from where the stack pointer currently is. Okay? And first of all, it actually subtracted 16 from the stack pointer. Okay? So it puts the two variables on there. All right. And then it just populates the arguments with the two values that we got. So we put the arguments into RSI and RDI because we know that RDI is the first, RSI is the second argument. And then we call our swap add function, okay, which goes, and I don't have the assembly up here, but it calls it, as you might imagine, and then everything happens. And then at the end of the function, it just knows that the result is going to be in this case, it was a long, so it's going to be an RAX. And it grabs the values off the stack and puts them in this case, does the subtraction and then does a multiplication on there as well. But you see how the values, when you have the ampersand, need to go on the stack. What questions do we have about that at this point? Anything? I see people going, okay, there and then there. That's good. All right. Okay, let us go on to this. Now, the other day, this is a very similar slide to what I had up the other day, but Julie and I talked, and we've decided that a better name, in fact, we're going to update the handout that gives the list of the types of registers. We're going to say that there are registers that are caller-owned and callee-owned. And we think that actually makes a little more sense for who gets to, who has to take care of the values when they're being used in the registers. So in other words, you've got these registers. In this case, we were talking about RBX is the one that we say never really got used before, because it's one of those ones that if you are in a function you want to use RBX, you have to save that value before you can use it, because the function that called you is the one who owns it. So does that make sense? We're saying that RBX, and in fact all of these, RBX, RBP, and then R12 through R15, are all what we're going to call caller-owned. In other words, the caller owns those. So if you are the callee function, you have to save them before you can use them. Does that make sense, Charlie? Yes, you save it by generally pushing it onto the stack. We'll see an example in a second. You push it onto the stack, and then once it's on the stack, then it's saved. And then at the end of the function, you just have to remember to remove it and put it back in RBX so that the calling function has the value that it expects. Question? Yeah. The caller owns it. In other words, the caller gets to put it in. The caller says, it's mine, and if you want to change it, it's your responsibility to change it. That's the notion we're going to. Yeah, you can borrow RBX. The callee can borrow RBX in that sense. Yeah, does that make sense? It's just a slight turn of phrase, and we're thinking of it a little differently than we talked about the other day, just because I think it's a little easier to kind of figure out, to remember in that case. Like if the caller owns it, then the callee better save it before moving things around. Yeah, here. Yeah, this is a good question. So in what circumstances would you decide whether or not to use a caller or a callee-owned variable? Okay, there are generally a couple different decisions you have to make. If you are using, you get to use all the callee-owned ones all you want, and you don't have to worry about them being in the same place. So if they're temporary variables that you need to use for now, just use them and forget about it. If you are calling another function, and that's pretty much the other option. If you're calling a function, where are you going to save your data in registers except for the caller-owned ones in that case? Now, you might say, oh, well, why don't I just push them on the stack? You could do that too and save them on the stack, but it's going to be faster with registers. So if you know which ones you have to use, and why are they split in half? Like why are there about half are callee-owned and about half are caller-owned? It's basically so that you can have this function passing idea where you get, hey, some registers are yours as the caller, some are as the callee, and it just shares the wealth in that case. Very good question. Yeah? And if it's passed by reference, does it always need to save it or store it? So the question is if it's passed by reference, anything that's passed by reference is going to be a memory address, right? And so then you just can't touch things that are on the stack unless you explicitly have them as arguments. Like if that's when you would modify that. Good question. Anybody else? Yes. Cynthia. Okay, so we're right. So there's the other ones, right? So we've got the caller-owned ones are here, and then we're saying that the other ones we callee-owned. Those are all the other ones. So our AX, our DX, our SI, our DI, all of those ones are the ones that are owned by the caller, or the callee, the one who gets called, and you can modify those all you want. Yeah. R10 and R11, now remember that the sheet that I passed out has a slightly different terminology, right? The R10 and R11 should be callee-owned. In other words, the callee gets to do whatever they want with them and doesn't have to worry about changing them. If the caller had something in those before they called the other function, they would have to move them before they called the function, or else they'd be possibility of being gone. That's the distinction.
So the sheet is corrected now, both of them?
Oh, the sheet is corrected online. The paper one isn't. Did you correct all the paper ones too? Oh, okay. Yeah. Sorry, they're both online now? Okay, thank you, Julie. Anybody else? All right. So that's how these work. Now, I showed this example, and I don't think I went through this one in enough detail. So I've broken this out into a little bit more detail as far as what's happening. We're going to walk through this one at a time. We're going to see how this actually happens with the callee-owned and the caller-owned registers. Okay? So let's see how this one works. Okay. When a function is called, if it's going to use any of the caller-owned registers, it saves them on the stack. So that's the first thing that this function, this long p function does. Okay, it's going to save RBP and RBX because it's about to use them in a couple instructions here. Okay, so it pushes those onto the stack, and they're saved for later. Okay, and then what has happened? What's going on here? All right, well, we know that RDI is which register? What argument is RDI? First one, right? So we're moving that into RBP. But let's look at our C function for a second and say, okay, what's happening here? P is calling another function Q with the variable y, okay? And it's going to, so we're going to need y to be in RDI. So if y is in RDI, then we better save our own, what we have in RDI now, because guess what? X originally was in RDI, and so we need to save it. And so where are we going to save it? We're going to save it in a caller-owned register so that we know that it will be there when the function returns. Does that make sense? So that's what's happening on this line here. We're saying, oh, look, we're about to use RDI because we're about to call a function, and if we're about to call a function, we'd better save RDI, what is in RDI, because we're about to replace it with what we need there for the calling function. Whew, it's a lot of words. Yes?
Is there any advantage or disadvantage to saving the values in the stack versus the caller register?
Right. The disadvantage to saving in the stack is just it's slower. Memory accesses are much, much slower than register accesses. Yeah, good question. All right, so that's what's happening here. Well, guess what? Now in the next one, we say, oh, OK, we're going to move I, which is RSI, into RDI because we're about to call a function that needs the value in RDI as its first argument. Right? Now, you might be thinking, well, you could do this much more efficiently. Well, you might be able to do this more efficiently in some way. You might be able to somehow tell the calling function that this is now the new first register. We need something that works every single time. First of all, because if you're going to write programs that other functions that other programs are going to use, it better have a baseline way of doing things. And so that's what's going on here. So you might say, oh, that seems a little inefficient. Well, it's efficient when it comes down to everybody has to be on the same page. Okay? So do you see how that one works? Hopefully that's becoming a little more clear now. All right, and then we call the function, and right now we know that y is in RDI. Okay, and when we get it back, it's going to be in RA. When we get the result back, it's going to be in RAX. Okay, and afterwards, then we're saying, okay, now look, we are going to have to move the result of the function that we just called into some other temporary caller-owned variable because we're about to call another function which is going to return the value in RAX. So the compiler has to think about all these things, right? The compiler has to do all this, like figuring out when it's going through the translating your C code into assembly code. Okay, so that's what's happening. It's kind of amazing that it does come out as efficient as it does, if you ask me. Okay, then what are we going to do? We're about to call the same function again, but now on X, which we already know was in RBP. So let's move that to RDI, which is our first argument for the calling function we're about to call. Okay, then we call the function, and then when we get back, we know that RAX has the result from this call, and therefore we can then go and do whatever we want. In this case, we're adding u plus v. Well, u, which was the value we just put in RBX, is now going to be added to the result which we just got back. So it's this big game of like shuffling things around so that everything works out when you call these functions. Question?
Slightly confused about where registers and stacks are. So for example, you first push RBP
Mm-hmm.
into the stack, and then on the third line, you move RDI to RBP. You move to like
This is a good question. And let me see if I got your question right. You're saying, wait, if I just pushed RBP, why am I then like setting some value? Remember what a push does. It copies the value out of RBP onto the stack, and then we are free to use RBP after that. So that's what's going. So when you say down here, move RDI to RBP, this is it's a register that you now have freed up because you've saved the value on the stack. Yeah, well, when you pop from the stack, it pops from where the stack pointer is, right? It takes it off where the stack pointer is and then decrements the stack pointer by 4, or 8 rather. Yes. Yep, and they're backwards. Yeah, good call. If you look, you first pushed on RBP and then pushed RBX, and at the end here, we'll get there in one instruction, we're going to pop RBX first because it's first in, first out thing. Very good. Yep.
So the point here is because RBP is a quarter state. So
Yep.
When we are calling the RBP actually belongs to the functions we call Q, so we cannot, right?
Yes, so the question is when we call function Q down here, when we call Q here and here, we have saved our value of RBP, some value in RBP and RBX that will not be changed because of the function that is called is guaranteed to not change it or replace it if it does change it, like put it back where it came from. So yes, that's the basic idea. Yeah. If there's nothing, there's always something in a register, right? A register always has some value. It might be 0, but it's always some value. So yeah, so it's there's nothing dangerous about it at all. It's just a matter of you're pushing, if it's a garbage value, then you pushed a garbage value, but you have no idea where you get it. Sonora?
What would you do if we were trying to call a function that took more parameters than we have extra registers?
Oh, yeah, we did cover this on Friday. If you're calling a function with more than 6 parameters, the other parameters go on the stack in a very orderly manner. And then you have to have another value that says how many there are. Well, actually, you don't. It says you just know how many you've pushed on because your function that gets called knows how many there should be. So you do have to store those ones on the stack. Yeah, good question. Yeah, Matthew?
You said the other day there was like some kind of convention of pushing for 8 bytes. Can you push EBP or something smaller, or is it always R that you're pushing? Like it's always 8 bytes and pushing copies from
I believe you can only, with the push operation, you can only push 8 bytes. There are push L. Oh, Julie's telling me there are push L and push K. Okay, so there's push L, push W, and all that. You can push them on. You have to be a little careful because then you're going to have alignment issues, which we'll get to a little bit later. But yeah, so you can push less than the full register on there. Yep.
Is there a reason that we use both RBP and RBX? Because it seems like
Yeah, I knew you'd ask about this, or somebody would.
we could first move RBP into RBI and then move RAX into RBP.
Sure. So remember how I said this was kind of magical how this efficient this ends up? It's not perfectly efficient, right? It's pretty darn good though. And this happens to be a relatively low optimization anyway. So given a little more optimization freedom, which we aren't doing in here because we want to show you something that makes sense, the compiler might just have done that. It went, oh, I did use that register. I don't need to use, I can do a little more swapping around where I only need one at a time. So it has to be, it can be a little more clever than that in general. Now, second guessing what the compiler does is a whole different ballgame. Like you can sit there and second guess these things all day. But the object of the compiler is A, to make it work the way you want it to. That's the first level of responsibility. And the second level is, hey, if I can make it faster or smaller or whatever, it's going to try to do that. Yeah, good question. Yeah. The push does do the subtract. Remember, the push does 2 things. It takes the value, puts it at the current stack pointer, and then reduces the stack pointer by 8. And then that's where the new stack pointer is. Yeah. All right, good. I'm glad I went over this because it sounds like there were still a lot of questions about it. So good. Okay, so where were we? We were about to pop the registers off. This is just restoring those caller-owned variables back, or variables, registers in this case, back to where they belong, so that when you do the return, you will end up, the calling function to P gets BP and BX back where it expects them. Yeah.
When you say restoring the variable, do you mean it's talk about the function pointer moving that back to where it was so that it
Oh, so be a little careful here. Okay, let's think about this for 1 second. When the function starts, right, what does the stack pointer point to when the function starts? This is actually a good question. When a function begins, where's the stack pointer right then? What is it pointing? What value is it pointing to? Does anybody remember this? This is a key point, actually. The first line after the call that called this function. I couldn't have said it better. First line after the call that called this function. That's what the stack pointer currently points at, that value. When you do the return, it better also still be than that current part. It still should be at the current stack pointer location. And so that's the end of it. So as long as you can do whatever you want with the stack below the stack pointer while you've got it, but at the end, stack pointer better be in the same place you found it, and all your registers should be back to the caller-owned one should be back to normal.
So pushing is moving the stack.
Pushing is moving the stack pointer, yes. And popping is moving it as well. So pop, remember, takes the value off and then, well, increments actually I think it's the other way around. It increments the stack pointer and then takes the value off it at that location.
So after the two pops, the stack pointer is back to what?
Yes, after the 2 pops, the stack pointer is back where it started. Yeah, good question. All right. Okay, so there we go. We've gotten that out of the way. All right, and back to where we are. All right, so a topic you know and love from CS 106B, right? Recursion. You spent hundreds of hours learning about recursion in 106B. We're just going to show you how it works. I'm just going to show you how it works now with assembly code, and there's nothing magical about it. In fact, you might even give it a little more enlightenment to what's actually happening here. Okay? So what do we have here? Well, first of all, remember, recursion is just a function calling itself. So if a function calls itself, it has to follow the same rules as calling any other function, which means that it is, in some sense, both the caller and the callee, and it has to take care of that in the appropriate place in the code. Okay? So I don't think I have this one. We could look at this one in general, but let's just look at it as we go along here, or as we see it. So this is a factorial function. Okay? It just basically takes in a value n and computes the factorial and returns that value. Okay? And how does it do it? Well, we'll look at the code in a second, but it basically just multiplies by n minus 1 until n becomes 1. Okay? And it does that using recursion right here. All right, let's see what happens in terms of the stack and in terms of the variables here. Okay? All right, so the function starts. And it says, OK, I am a callee in this case, so I had better store rbx if I'm about to use it. OK? All right, and then it immediately moves the value that it got in RDI into rbx, because it's going to use that at the end, as it turns out, to do the multiplication. OK? All right, and then it moves, then it does this. So it actually is a little, this came out a little bit weird. The move is right there for the return value. The compare is actually here. So it actually did something a little clever, but looks a little backwards the way it does it. But the compare for the if n is less than or equal to 1 happens right here. And then this one's a little different than some of the other if statements we've seen before. It actually does jump if less than to, in this case, all the way down here, which is the actual return part. Okay, so basically set the result up here and then does the test. So it's just a little bit out of order we might think of it in C. But that's that. Okay, so if it doesn't, if the value is not less than or equal to 1, what does it do? Well, it subtracts what? It actually subtracts 1, right? And then puts the value in RDI. That's a little weird too. You might want to do a move or something, but it works just fine. Okay, and then it calls the r factorial. All right, so what do we know at this point? Well, we've stored a value of bpx, and then we're about to call the function again and repeat the process. Okay, and it calls itself, which means it starts back up here again. And what happens? Well, our bx, now or again, we're a callee function, so we better save those caller-owned variables. And so we'd save it, move the value for n we got, and do it. So what's happening here? It's basically saving all the values of n minus 1, and n minus 2, n minus 3, n minus 4 on the stack, and it's about to pop them all off and do the multiplication. Okay? So let's assume we've done that a bunch of times, and we get down to here, and we've now said, okay, now what we got passed in was less than or equal to 1. Okay, we jump down here, and we immediately pop the value that we stored on there. We don't need to pop the 1, actually doesn't matter, because we don't need to multiply by 1, as it turns out. And then that pops, and then it returns to where? It returns to right here in the previous function that called it. Make sense? And then what does it do? Well, it says, okay, I saved RBX earlier, which got returned to me, and then I just stored the value earlier that I was, it actually stored, sorry, it stores the value, originally stored 1, and now it's going to multiply by that other value and that we just got back, and then that's going to be in RAX as it returns to where? It returns to the same line in the previous called function. So it ends up doing a bunch of multiplications all at once. Like it multiplies, returns, multiplies, returns, multiplies, returns. It's kind of cool that way. Yeah, Shravya. Well, right. So you could do this with another variable, except that it doesn't necessarily, well, yeah, when you get it, you just know that RBX is going to be the same when you get back. So if you store something in RBX, that's when you then end up using it. Now in this case, yeah, sure, it's pushing on RBX. It could have pushed on some of it, but it wouldn't necessarily need to push on RBX if it's not going to use it. It would just use some other register that's caller owned anyway. And so so it does, in this case, the only reason we used RBX is because we're about to save something in RBX for later. So yeah, you could rethink this and hand code this in some other way that's probably just about as efficient. Yeah. Yeah.
So after you do the call and multiply, then you fall through to the prompt, right? After all the
So yeah, sorry, after you do the call and then the multiply, what happens? Well, you're back to popping the next value off the stack. Yeah, sorry, I missed that part. Popping the next value off the stack. So it multiplies, pops, multiplies, pops, multiplies, pops, returns, multiplies, pops, returns, right? Does the multiplication, pops the value, returns. And if you walk through the whole call tree about this, you'll see that it's actually doing exactly what we thought. Putting the values, pushing all the n minus 1, n minus 2, n minus 3 onto the stack, and then reversing the process and doing all those multiplications at the end. Yeah, Matthias.
Stack overflow, you think when we do a lot of calls like this,
Yeah.
would be the uncontested like push queue many times that keeps popping onto the stack until the stack is distributed?
Yeah, this is a good question. So when you are given a certain amount of memory for your stack, it's a limited amount of memory, right? And it's actually defined by the operating system that when a program gets run, you only get so much memory in the stack. And if you did this value where, or if you did this for some value that was too big and you had to call it too many times, you'd constantly be pushing on here, which constantly decrements the stack, and eventually it decrements too far and you get a seg fault because you've decremented the stack pointer too far past the area you own. Yeah. Yes?
Doesn't IMOP always multiply RAX by the factors?
Which version of multiplication is this one? The 1 operand, 2 operand, or, well, there's also a 3, but the 1 or the 2 are the ones we care about. This one's a 2 operand one. So you have to pass in 2 operands. So it's always going to multiply RBX, the source, times the destination, and put the result in the destination. Yeah. There's another one where you just have IMO, Q, and then percent RBX, which always multiplies that one by RAX, RDX pair. And then, or sorry, RAX, and then puts that into the. Oh, that right. It's a different operation, as it turns out, in the underlying code. It looks the same in text because they're both multiplication, so we just called it the same thing. But under the hood, the actual operation is different. Yeah, good question. All right. Anybody else? All right. So that's recursion. You may see more of this in the coming week. Hint, hint. All right. So let's move on to array allocation. All right. We've been talking about arrays on and off in the whole class here. What's very cool is that arrays in C map pretty well to x86 assembly code. This is not necessarily true in some other machine code, although many machine languages are built around the idea that, oh, we're probably going to use a lot of arrays, so they build these things into the actual architecture, so the instruction set itself. When we perform integer arithmetic, the assembly code itself that's produced is going to have the computations built into them. In other words, all of the idea of, oh, here's an index into our value and all that, and here's the name of the array, all goes out the window when we get to assembly code. You'll see how it works. And so reverse engineering arrays can be a little bit tricky because you have to see the big picture and see how it works. We'll show you how it goes, and I think you'll start to pick up on it. But it does take a little bit of time to figure it out. Now, optimizing compilers, very, very, very good at simplifying the address computations. It will take a look at it, and it will go, oh, OK, I'm going to see how we're going to practice some in a minute or two. And you're going to see how this actually goes and works. The array computations don't always look like what you're expecting. Okay? Now, you saw this in lab when and in the assignment where you did divide, right? If we're dividing by an integer of some sort, the compiler is going to figure out some way to avoid actually doing a divide instruction because divides are slow. And if it can do a shift or if it can do some other fancier kind of arithmetic that doesn't involve divides, that's what it's going to do. Well, it's similar vein here in the sense that you'll see things that the compiler's created referencing your arrays, and you go, oh, I got to figure out what it actually did to get that value. Okay? You'll see. Just bear with it and learn how to do it. Okay, so here's how arrays work. We're going to declare an array, and to do that, we know about this, right? We have a type, and we have some number of elements that are going to the array, and we have some name in this case. Okay, so it's type, and then name, and then bracket, and then that. And that declares n times the size of t bytes, contiguous, and it does that generally on the stack, actually, as it turns out. And it gives us some identifier that we can use as a pointer. Now remember, it's not a pointer. Be a little careful with that, but we know all about that now. And then we're going to call this starting value, which is pointing to the beginning of the array. Right? That's the address of the beginning of those bytes that we were given, x sub a. Okay? So that's what it's called. All right. Here's how it actually looks when you break it out a little bit. So let's take some examples. Char A12. Well, each char is 1 byte long. Okay? So a total of 12 bytes. And we're going to just call the starting address x sub a. And then element I is just xa plus I away from it, because each one is 1 byte away. All right, so far so good. All right, how about this one? Char pointer B 8. Well, we know it's holding char pointers, which are each 8 bytes long. Therefore, if there's 8 bytes and we're doing an array of size 8, there's 64 total bytes. Okay, we're going to call that starting address xb. And now here's the interesting part. What is the address of each subsequent element? Well, it's 8 more because each pointer is 8 bytes long, so it's xb plus 8 times whatever that index is. Remember, you've got to do the scaling. Okay, this is where the scaling happens in the code. Okay, same thing for an integer array of 6 elements, right? It's going to have each element is 4 bytes. It's going to be 24 total, xc, and then xc plus 4 i's for the scaling. All pointers are going to give you the same exact type of value for the element size, and then just total sizes times the number of elements. Okay? Pretty straightforward, hopefully? Okay? So the memory addressing, remember, we've got all those cool memory addressing operations that we talked about way back on the first day of assembly that you've grown to love now that allow us to do all sorts of cool array indexing. Okay, so if we wanted to access C bracket 3 above, right? Well, let's see. C is an integer array, okay? If the address of C was in RDX and the index 3 was held in RCX, what would we have to do, right? If we wanted to move the value into, say, another register, well, we could say, okay, RDX plus 4 times RCX, which is the actual scaling up here. See how that works? It's not too bad once you get to this point. Okay? All right. Okay. Here's some more examples. We'll go through a few of these, and then we'll actually try some together. Okay? All right. So let's say we have a some value, some array E. Okay? And we are going to have, in this case, I believe it is a, yeah, it is actually a char pointer in this case. Okay? What's that? Oh, it is an int pointer, sorry, because of the extra 4s in here, yes. Okay, so what are we going to do here? We're going to, yeah, sorry, it's an int pointer. I'm looking at it right here. Okay, so if we have the expression E, which refers to the address of the array, right, it's just going to be value xe. And if we want to move that into RAX, how do we do it? Well, we move the long, in this case, right, RDX into RAX. Okay, wait, does that make sense? Should be move Q, shouldn't it? It should be move Q in that case. That doesn't make sense. I'll just change that. Okay, so it's going to be moving Q into RDX into RAX. Okay? All right, if we want the element at location 0, well, that's going to be memory, going to memory, getting the location at E, and in this case, now we can move L because it's moving a 4-byte element from RDX, the memory address at RDX, which is where E lives, into, in this case, EAX. Julie's furiously checking all mine now to see if to make their sense. Thank you. All right, so let's look at a different one. If we have index I, well, then we need to do the scaling for this, right? For integers, we scale by 4. And in this case, we're still getting a memory address. The type of this thing is an int. We are going to get the memory address of the original plus 4 times I. How do we do that? We now move RDX plus 4 times RCX into EAX. Good? All right, let's do a couple more. If we want to do the address of the element at index 2, what do we do? Well, first of all, it's an int pointer. Okay, it's going to be just xe plus 8, y 8, because it's 4 times 2. Okay? And then in this case, we only want the address, so we're going to use the LEAQ instruction to move that address from RDX, 8 away from RDX, into RAX. Good? All right. All right. And then the same thing for all these other ones. You have to just do the scaling as you go along. Try me. How would you do the address? How would you do the address of this one? So if you wanted to find like the address of this whole thing, I guess, like that, you mean? This one, is that what you mean? This is what's in the array. Sorry. Then you would have to then do a move instead of an LEAQ in that case, right? You'd have to do the move instruction because you want to access the variable, the register value. Good. Let's do this one. Okay. So if it was E plus I minus 1, all right. Well, you have to scale both the E and the I. Right? So you're going to have xe plus 4 times I minus 4, because that will back it up from I minus 1 in this case. And how do you do that? Well, you use the extra little, I'm going to, oh, there should be a, that's a negative, should be a negative on there, I think. No, it should not, sorry. This one is, oh, this one does extra math. This one, I'm looking at this one. This one, so in this one, what do we have? We've got, right, we've got RDX plus 4 times RCX plus another 4. So I believe that should be a minus. Yeah, sorry, I did see it right the first time. That should be a minus. I'll fix these and put them back up online. Sorry about the weirdness. All right, and then, yeah, question. Would it ever just subtract 1 from RCX? No, you have to scale it still, right? Well, okay, sometimes you might have to do a couple instructions, right, for some of these. You might have an extra instruction in there if you're going to have to do something that they can't figure out how to do it in one instruction. But yeah, in that case, you might do that. But in this case, yeah, I mean, it might do that first and then do the other thing, yeah. Question?
When you say the integer index I is an RCX, you just mean that the register RCX is a placeholder for.
It means that so let's say you have some variable I, which is your index. You're going to store it in a register maybe. Right. Yeah, the value 4. Right, if you're doing a loop, where are you keeping that loop variable? Probably in a register, right? The value of I is going to be in that register. That's the idea, yeah, for this one. Okay, you want to look at this one? This one looks a little crazy. This one is, so we're dereferencing, so we're going to use a move, and then we're going to do e plus I minus 3. Okay, in this case, you have to say, all right, again, we need to scale everybody by 3. This kind of reminds me of doing like chemistry balancing sort of things where you have to like figure out how to do the I know, I heard some, oh, I don't like that. This kind of reminds me of that a little. I never liked it either. But that's kind of what it reminds me of, doing a little bit of that. So what are we doing here? We're saying, okay, look, it's going to be xe plus 4 times I minus 4 times negative 3. Well, you can bring that negative 12 out front here, and you have to do this kind of like arithmetic to figure it out, because you've got r dx plus 4 times rcx, right? And then you have to subtract away the 12 from it. A little trickier. All right. And then this one's just saying, hey, look, if you really wanted to find the address of the value, the difference between, for I, you basically do a move where you're just doing RCX into RAX. That's what's happening there. Okay, you want to try some? Here we go. Let's set this up. Address. XS is the address of a short. How many bytes are shorts? 2 bytes. Okay, let's keep that in mind. Okay, again, we're going to store the address in RDX, and we're going to store the index in RCX. Okay, all right. So let's do a couple of these here. All right. So if we want s plus 1, is that going to be an array or an address or a short? It's going to be an address. So it's going to be a short address. Okay. And the value that we're going to get is just going to be xs plus what? 2, because we have to scale it, right? So in this case, if we're going to do that, we're going to use LEAQ, okay? And then we're going to have the scaling happen kind of outside, but let's do this, percent RDX, right? And then we can add the 2 to it that way, okay? And then you're going to move that into percent RAX. Make sense how we do that? Okay, let's look at another one. What's the type of this one going to be? Just a short, right? That was going to be a short. And then the value, we're going to have this in memory here. We're going to get the value at what location? It's going to be xs plus something. 6 in this case because we're scaling them by 2. Remember, we're scaling shorts by 2. Okay, this one's going to be a move. What's the suffix going to be on here for moving bytes? I'm sorry, word, 2-byte words. W, right? W. Okay, and then we're going to scale it by 6. Percent RDX, and then we're going to do percent RAX. Good. Okay. How about? Thank you. It's not going to be percent RAX, is it? What is it going to be? Just AX. Thank you. I go too fast on these. There we go. Percent AX because we're moving to a word, a 2-byte word. Good point that we're trying to move what we want to move, and the suffix tells us. Yeah. Yeah, this is a good question. If you care about the upper bytes of AX, then you would do a ZWQ in that case to zero those out. Yeah, move ZWQ. Yeah, could have done that if you cared about it. Okay. All right. And in this case, just said the result should be in register AX, so we're not too worried about doing that. Okay, let's look at another one. The address of I in this case. This is going to be a short pointer, right? And so therefore, we're going to just do xs plus what? 2 times I, right? Well, how do we do that? How about LEAQ again? Okay. And then in this one, we need to do the adding kind of at the end, or the adding at the end, right? So we're going to do 2 Oh, sorry, we're not going to do it at the end. We're going to do it in the middle, aren't we? We're going to do, there we go. Oops, there we go. We're going to do that. Percent RDX. Okay, now we're going to use I, which is percent RCX, and now we're going to multiply it by 2. And then this one, because it's an address, we can put it into percent RAX. Okay, let's do another one. This one going to be a memory or just a short? Just a short. Okay, so it's going to be a memory of what in this case? XS plus, okay, how many times I? 8 times I. Why 8? Because we're doing 4 over here, so it's going to be 2. So it's going to be 8I, and then how much more? Plus 2 more, because we're doing 1 times the 2 from the short here. Okay, this one's going to be another move, W. Okay, and then in this case, this is another one where you're going to have to do a little bit of arithmetic to figure this out. Okay, let's do the scaling for the, well, let me just write down what it comes out to be. You could probably figure it out. 10, nope, sorry, I'm doing the wrong one again. I'm looking at the wrong one on my sheet. Sorry, move W, 2 rather for this one, and then percent RDX, and then percent RCX, right? And then we have the 8, which is going to scale that one, and then to percent what? AX. Okay, last one. Now I'm on the right page. Okay, this one is just going to be a short pointer. And we are going to do, it's going to be XS plus, how many here? 2I plus, well, should say minus, plus negative 10, I guess. All right? Okay, and this one's the one where we're going to do LEAQ, and then minus 10, and then percent, oh, am I going too low? Sorry. Percent RDX, and then, oops, my pen is giving me trouble here, and then percent RCX, and then we've got how many we're going to scale this one by? 2, because we need to, we're going to have the minus 10 at the end there, and then this goes into percent RAX. Whew. Okay, let me make sure that you see those in real typing in that case. And that's how they end up. So these are a little bit tricky, but if you see something like this bottom one here, you're going to have to do a little bit of like thinking to reverse engineer it. Okay? All right, question.
Is it convention to have the address of the base on the left when you're adding on the left?
It is convention to have the address of the base over here because you're generally going to index into that by some scaling factor. Remember, this is really the scaling factor here. Okay. All right. All right. All of that, take a break. 3 minutes. Okay, there we are. As we come back, I forgot to mention this at the beginning. If you want regrades for the midterm, please put them in today because Julie and I are going to look at those in the next day or so and try to get those grades looked at again for you. Okay, so please put them in today for your midterm regrades if you want to do them. And to do that, send an email to cs107@cs.stanford.edu, and we will take a look. Okay, all right, so we've talked about arrays. Let's talk briefly about structs. Now, what's a struct? Well, you learned about structs in 106B, and then we've talked very briefly about structs in this class as well. But a struct basically is this idea of grouping a bunch of things together of different types so that you can use them as a unit, okay? The follow-on to structs in other languages is generally objects, which not only include data but also include functions. But in our case, structs just include data, and they have fields in them, and they use dot notation and arrow notation if you have a pointer, and that should be, relatively, you should have already seen this in maybe some other class. If not, they're not that hard to learn about. But the idea is of structures, a couple interesting things about them. They are kept in contiguous memory. Okay, so if you have a struct, all of the fields have to be contiguous relative to each other. Okay, and what it also means in that case is that you can't have two pointers in there. Or sorry, you can't have two. You can have two pointers, but they won't be. They point to somewhere else, but the pointers themselves are continuous. You had a question?
So in struct, do all of the fields have to have a value? So does that
all the structs have to have a value? Well, they'd use as much memory as you've given them. So yeah, if you don't, the act of saying I want this struct gives you the entire space for the entire struct. Yeah, good question. Okay, so what we do is that we create a struct and then we give a pointer, as you can imagine, to the first byte. It's just like an array. We get a pointer to the first byte, and then the compiler keeps byte offsets for each field. Okay, so it knows that if you've got an int, you're going to have 4 bytes. Then if you have another char after that, you've got 1 byte, and so on and so forth. And it keeps those as it's creating your assembly program and populates the addressing appropriately. Okay, so we have these byte offsets, which are going to give us the things that we're looking for. Okay, so let's look at an example. Here's an example of a struct. Okay, a struct called REC, and it has an int and then another int, and then an array of 2 ints, and then it's got an int pointer as well. Okay, and if you look at the contents of what the compiler actually creates, it's going to look like this in memory. It's going to be contiguous, and it's going to have bytes 0 through 3 are going to be I, and then 4 through 7 are going to be J, and then 8 through 11 are going to be A bracket 0, 12 through 15 are A1, and then 16 through 23 are the value for this pointer, which is 8 bytes long. What's interesting about this is, oh, guess what? Our array is actually embedded inside this struct. Okay, you can still reference it as a pointer and so forth, but it's actually embedded in there. It's not like the array is a pointer to some other place in memory that has the struct. Okay, so that's kind of interesting. Okay, again, these are the offsets up here, and then the field values down here, the names down here. Okay, the field offsets are where we get. So the compiler will know that J is offset 4 from I, and it will know that A1 is offset 12 from the beginning of the struct. Okay, all right. So let's take a look at an example here. All right, some of these examples are a little hokey, as it turns out, but you'll see what happens here. So if we have, again, now in this case, RDI is our struct pointer. Okay? The following code will copy RI into RJ. Maybe you want to do that for some reason. Okay, well, what do? We first move the value from RI into EAX. Okay, how do we do that? We do a move L because it's an 4-byte integer. Okay, and then we move EAX into, oh, look, there's our offset of J, 4, from the original RDI location. Not too bad, I hope. Everybody with me on that one? Okay, all right. You can generate a pointer to the field by the offset to that struct. Okay, you just need to add the offset to that the original struct pointer. It's just like getting the address of an array. You just have to know what the actual address is itself. Okay, so in this case, we're going to kind of do a little bit like 2 things here. We're going to say, okay, now we're going to generate the address of RA1. That's the address here. Okay, now let's see if this actually works. All right, it's going to do RDI, which is where we said that the beginning lived, in RDI. Okay, that's the address of the beginning of the struct. And then in this case, we have the int variable I into the addressing of this case. Okay, so we're going to look for AI. We're going to generate the pointer value R bracket AI by, well, sorry, it's not, I guess it's not 12. It's either 8 or 12, depending on what it is, by doing a little bit of this same math as we always do. Right? We're going to take RDI, and we're going to do RSI. We're going to scale it by, in this case, 4, because the arrays are integers, 4 bytes, and we have to offset that by the original offset, which was 8 to the beginning of A0. There's a lot going on there. Yes?
Are the contents of a struct always stored in memory in the order that they're declared?
That's a very good question. That's like a bonus good question. Yes, the variables are always stored in the order. The fields are stored in the order you define them. Yep, they have to be stored in that order. Now, you could think of a case where the compiler goes, oh, maybe I'll store it in a different order, and we'll see why that actually becomes a little bit problematic in another slide or two. But yeah, that's a good point. Okay, now, I think the next slide is the hokiest of the hokey ones here. Okay, let's say that, oh, question. Yes. Yeah, this is a good question. So would you bother with this? In this case, the reason we had to bother with this, do it this way, was because the I here, we didn't know that beforehand. If it knew it was looking for RA1, it would go straight to that one. It would go straight and put 12 there as the offset. It would know, it would calculate that ahead of time. But in this case, it just says, I don't really know what it is, but I do know that indices int arrays are 4 bytes each, so I can scale it appropriately. Make sense? All right, good. All right, let's look at this next one, which I said is kind of the hokey one. Let's say, for some reason, we wanted to put the address of ARI plus RJ into RP. And you go, wow, why would I want to do that? Well, I don't know, maybe you want to do that for some reason. There's probably a real example under here somewhere. Let's say we want to do that. Here's how we might do it. Okay, let's walk through this. Move L. So first we're going to get RJ, let's say. Maybe we could have gotten RI first, doesn't really matter. But let's get RJ. Well, how do we do that? We offset 4 from RDI, which holds the beginning. That's RDI. Okay, and we put that into EAX. Okay, so in this case, whatever that value, J, is now in EAX. And then we add the memory that we get from the value that is at I, because it's no offset. You can think of this as just a 1 offset there. Okay, I'm sorry, a 0 offset there. What am I doing? A 0 offset there. And you then add those together. Okay, then we do this, and we say, well, CLTQ. That's extend. Remember, that's the extension command that extends EAX into the entire RDX variable. It does a sign extension. Why do we do that? Well, we're about to put it into an 8-byte long area, so we're going, field, so we're going to need to do that. And then we do the computation, which we need to do kind of first here because we can't do it all in one memory. We have to do the computation, which says, okay, now we know that we just put the value RAX in here, okay? And we are going to take RAX, and we are going to find the memory address of RAX times 4, right? Because they're 4 bytes long. And that's going to give us how many down the array we are. Okay? And then we add that to the original, and then we add it to the 8, which is the beginning of this array. There's a lot going on in that one. Sit down and look at that one if you haven't quite figured it out yet. All right. Any questions on that one? It's not too bad. It's just a lot of like, hey, I'm trying to figure out exactly what I had based on the original original registers that we have. Okay. So, yeah. Because I have a autocorrect, and it should be what? In this case, it should be Q, yes. It always does that, and I try to catch them every time I do that, but it should be that, yes. Good question. Good catch. All right. So you'll notice that all the struct manipulation is handled at compile time, if it can. Now, sometimes it can't figure out indexing into arrays because you've given it an index value in another register. But it happens at compile time to the extent that it can, and all of the variable names and all the offsets are pretty much gone by the time it gets into the code. So again, reverse engineering this is a little bit tricky because of that. The compiler has to do all that work, and you might say, "Oh man, it's got to have some pretty good logic to do all that work." It does have some very good logic, and this gives me a chance to pitch CS143. If you like this stuff, if you hate this stuff, stay away from it maybe. But if you like this stuff, actually, what I can say about about a compiler's class, it really you all of a sudden learn how you learn how this happens. This translation from your C code into the assembly code, and it's quite fascinating how that actually gets transformed. Okay, one of my favorite classes in graduate school was compiler's class. I was I was completely confused for about the first month and a half. But after that, I said, oh, this is really pretty cool. But it all involves how does this stuff happen? How does the compiler figure this out? How does it do those optimizations? That's probably not going to happen. You're not going to learn too much about that in an intro compilers class. But you learn about the basics of how does it actually happen when you're, like, how does the translation happen? And how does it know what your variables are saying? And where does it keep this? And what kind of tables does it hold? It's quite kind of fascinating if you like that. So I think keep that in mind, that you will be ready for that after studying all this assembly language. Okay. So another thing we have to talk about is data alignment. Okay? So it turns out that computers often are built, their architectures are built with restrictions on where you can put values, say, on the stack. Okay? It wants them what we call aligned so that the address of the thing we're looking for, the actual value we're looking for, is on a boundary that might be divisible by 2, 4, 8, or some other number according to your hardware. Now, why does it do that? It's because the hardware is simplified that way. It turns out it doesn't have to do some other offset calculations, and it can grab values one word at a time from memory, and that's actually very fast if it's done that way. Most systems won't break if you don't do it, but it will be slower if you don't align these things. Okay? In some cases it does break, and you have to know which computer, if you're building a computer or if you're building a program that has those restrictions, you have to know that. But it's nice to know what the recommendations are. Okay? So Intel happens to recommend the following alignments in this case. Okay? It says, look, chars, we can just put those anywhere. It doesn't have to have any particular place, although on stacks, a lot of times we still align them so the next thing can be aligned properly. But it generally doesn't matter. Shorts are 2, ints and floats are 4, and 8s and longs, doubles, and char stars, or pointers in general, are on the 8-byte alignment. In other words, if you have a long, you should align it so that its address is divisible by 8. So a lot of times you'll see the compiler do this. And you'll go, what's going on? Why did it move that? Or why did it add an extra to that? Why did it add a little bit extra or subtract a little bit more from the stack pointer than it needed? Probably because it was trying to align these so that it's faster. It's an optimization. Yes?
Is this just a stack thing, or is it also a heap thing, and is it also a read or memory thing? Like, is it always trying to do multiple?
Yeah, that's a lot of questions all at once. Is it always a stack? So heap gets aligned to some extent. Stack gets aligned. Read-only memory is, I mean, it's anything that's going to touch the main memory, which all those do. It's going to probably align them based on the recommendations. That's what the goal is going to be, right? Now, you can fool around with the compiler settings or the flags and say, don't align them or do align them or so forth, and it will do the best to follow your rules unless it happens to be instructions that require that. Okay? Some of the floating point instructions, the memory locations must be aligned, otherwise it won't give you the right result. And Intel tells you that in the instructions. Yeah, Olivia. Yeah, Olivia, that is a perfect question. Take a look right here. Here's why it's a perfect question, because that's exactly right. If you don't have your struct aligned properly, the compiler might just go ahead and align it for you. And it might say, oh, all right, let's see what we've got here. We've got a struct where we've got an integer followed by a char, and then we've got another integer. But if I did that like this, then the second integer here will not be aligned according to the recommendations. So what does it do? It actually gives you some padding in here, and it makes your struct a little bit bigger than you thought it should be. Right? You can tell the compiler don't do that, but the compiler is going to do it because it's probably going to be faster. Now, it'll use up a little more memory. Now, maybe you'll tell the compiler, don't do this because I'm going to have a billion of these, and I don't want to waste 3, 4 bytes, or in this case, 3 bytes each time. Yeah?
And then if you were indexing within your struct, would it automatically do that?
Yes, and when you're indexing into it, because remember, the compiler keeps track of the 0, the 4, and the 5 here, and the 8 here, so it knows what the offsets are, and it just scales those offsets. It just uses those offsets appropriately. Yep. Now, the other thing is, the nice thing is, if it's doing the scaling, if it's aligned properly, it can probably figure out a better scaling for it too, which is another nice thing based on the offset. So it can do some of that chemical balancing sort of stuff I was talking about earlier, a little easier. Yeah, good question. All right, but does that make sense? So what that means is when you do size of, you might get a size of that isn't the addition of how many bytes this takes, how many bytes this takes, how many bytes this take, even though that's what you might expect. And that's how size of works on structs, by the way. Calculates how big the entire struct is, number of bytes for all the different fields. Yeah?
So then what's a reliable way to determine size of?
You still can use size of. I'm just saying that if you expected your size of to give you the value of 4 plus 1 plus 4, it's not going to in this case because it might have added this padding in there. Okay, so if you're doing generic functions, always just pass in the size of your struct. Don't try to second guess the compiler as far as what it's doing. Don't say, oh, I know that's 3 things. Yeah. Yep. Why doesn't the padding happen with the first int? Why doesn't the padding after? Well, it doesn't really matter at that case. The next struct might be placed on a boundary that it needs appropriately. Yeah, good question, Shravi. Yeah, this is a good question. When you're indexing into it, yes, if you tried to do it manually, like if you're trying to second guess and say, oh, I know it's 6 bytes ahead of here, then you're going to be in trouble if you don't, you just want the compiler to take care of it in that case. Don't try to second guess it. Somebody else had a question? Yeah. Well, when you're doing your C program, right, you're going to still access J, and where's J going to be? Well, the compiler knows that it put it here, so it's going to calculate that for you. You don't need to worry about that. The idea of showing you this is to say, hey, look, size of might not be where you think it should be, number one, and number two, hey, this alignment makes a difference, so the compiler tries to do it. Yeah, good. Okay, all right. Function pointers. So, remember how we did a bunch of function pointer things for the last assignment, and you guys passed along functions and it has this weird syntax, and you learned all about that, and then we did it on the midterm and so forth, right? What I wanted to do was, in fact, I thought this would be a good chance to go back and look at the program that Julie did in class in lecture 9, which was this max program that was gfind max. What's nice is that we have gotten through 4 days of this stuff, and when you see the code for this, you're going to be able to recognize a whole bunch of what's going on right now. Okay, so let's take a look at it. What I wanted to point out about the function pointers before we actually look at that is that the function pointer, there is a specific syntax for calling a function, which has call and then asterisk, which is kind of nice. It's like it's dereferencing, and that's an actual assembly function that assembly language instruction that we'll see that uses the address of whatever it's looking at to jump to do the call to. Okay, so let's actually take a look at this, and we'll just kind of go through and see what it actually looks like. I'm going to use GDB-TUI. Now, in lab and in the assignment, Julie's going to suggest that you might not use GDB-TUI. I'm going to use it because I'm going to have more things on the screen. I like to run it with GDB-TUI just like this instead of trying to start TUI in the program. I think it works a little bit better. But this is the max function. Okay, if we do layout and split, okay, it will give us the max function. Now, remember what this function does. It takes your command line arguments, and in fact, I've updated it to do what you had to do on the midterm, which is shift not worry about the first command line argument. Okay, I'll show it to you again. It actually it does this. It does the argc minus 1 and then argv plus 1 there. Okay, so keep that in mind when you're looking at this. And we are going to run it, in this case, with, let's say, A, B, C, D, E, F, B, 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 I don't know, F, G, G, whatever, and it will do that. Okay? Oops, before I do that, I want to break somewhere so it doesn't run, so it runs properly. Let's break right on main. And then run A, B, C, D, E, F, B, 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 F, 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 whatever. Okay, and there we go. Okay, all right, so you guys know what's going on here. What's happening at the beginning of this main function? What's going on here? Something is going on. We don't know exactly what it's going to be doing yet, but what's it doing right now? Adjusting the stack pointer, right? It's adjusting the stack pointer, so we know that that's maybe, it's going to use that in a minute. Okay, LEA -1 from RDI. Oh, well, what's going on here? RDI is the first argument, okay? I'm sorry, the RDI is the RDI is what? The first argument or the second argument? First argument, okay. So it's subtracting 1 from there, and that's going to be up here for the no, it's not in this case. Yeah, it is. Oh, it's doing the first argument. Yep, sorry. I'm up here. You're right. Thank you. It's doing the first argument. It's up, and I'm looking at the wrong part here. Okay, so it's doing that, and then it's subtracting that, and then it's going to do the same. It's going to move the what? In this case, it's going to move the pointer to a pointer that's 1 away from argv, right? It's going to move the second argument address into RDI, okay, because it's going to do that. And then it's going to move this weird value here. Let's look at what's there. I'm going to guess that there's a function there. It's saying that it's moving the CMP alpha, because that's our CX as it turns out. So if we do disassemble and then, let's see, disassemble 0x40059D. Oh, there it is. It's the compare alpha function. So that's nice. How did I see that? It came up here and it showed it right there. That's the compare alpha function. Okay, let's keep going here. Okay, and then it's going to move, in this case, 8 into EDX. Well, where'd the 8 come from? That's the size of the pointer. Okay, we know that now. You can kind of follow along here, right? Okay, and then it's going to move EAX, which is the value that we had already calculated, the argc minus 1, into ESI for our next argument. Okay, all right, and then it's going to call find max. Okay, so it calls find max, and we are in here. It's doing a bunch of pushing here. It's doing a bunch of pushing because it's probably going to call another function, and it's going to need to save a bunch of things on the stack. Well, why is it? And it's also going to be doing what? It's going to be doing a bunch of void pointers and things that it's going to be trying to push. So it's going to have some pointers, so it's going to need to be able to do that and store these values and so forth. Okay, all right, and then there's the stack operation there. Okay, and then we've got now we're doing the actual looping and things. And let's see, I'm just going to step through a lot of this stuff. Okay, and then this is the loop, and then we've got a jump, and then there's a comparison for the actual loop comparison, which you can have now. Okay, it's going to jump because of the loop comparison, and then, all right, we're getting there. Now it's going to actually do our compare function. Well, it's got to do some setup, right? It's got to set up some pointers. It saved the base pointer, or it saved EBX and the base pointer, okay? And then it's going to do the multiplication for I times element size, all right? And then it's going to add I guess it's going to be the value we stored for the array in there, and then it's going to move the proper variable, or move the proper values into the arguments, SI and SDI, or RDI, and then guess what? Look what it's doing. It's calling the memory address. It's going to register R15 saying, what memory address is that? And then it's going to call the memory address located in R15. That's where it's going to jump to next. Okay? And if we do that, we would actually see that it's exactly the same one we looked at earlier, and then it's in our comparison function. Okay? So you see how this is there's a lot going on here, but at this point you guys kind of know a lot of this stuff. And if I went a little slower, you'd be able to go through and kind of process it all. Yeah? Oh, this is a good question. The base pointer, and as far as we're concerned, the base pointer is another register we get to use that's call our own. That's about all you need to really worry about. It used to point to the base of the segment, and it was in some older architecture, so it's a little bit of historical kind of stuff that's still around. Yeah. All right. Any last minute questions on some of this assembly things? Yeah. The star meant get the address that's in that register and make that where we're calling to. It's the function pointer. That was where the function pointer came from. The star was, that R15 was where the star pointer, the function pointer was located. That address was the address of the pointer in code that it goes to, jumps to. All right, see you guys Friday.